Echo Whiskey, Roger. Join downwind left hand, runway 26, Quebec Foxtrot Echo.
In level flight, at steady speed, lift equals weight and thrust equals drag. Lift and weight are about 8 times greater than thrust and drag, but for clarity's sake, we've reduced this ratio in the diagram. So we have two unequal pairs of forces acting at right angles to one another. But suppose we want to climb or descend. What happens to the forces then? As the nose pitches up, the picture changes. 3 of the forces, lift, thrust, and drag, are in the same relationship to the flight path in the climb as they were in level flight. Weight, however, still acts vertically downwards, and so is now at an angle to the flight path, downwards and backwards. It is thus augmenting drag. This directional effect of weight on drag slows the aeroplane down in the climb, so that both lift and aerodynamic drag are reduced. But if we add the drag effect of weight to the remaining aerodynamic drag, the total drag becomes greater than in level flight. To keep the forces in balance, thrust must be increased to balance the new force of drag plus its component of weight. Change from a climb to a descent, and weight, still acting vertically downwards, is now augmenting thrust. The aeroplane will accelerate, lift and drag will increase. So to keep the forces in balance, we must reduce thrust to allow drag to balance the force of weight acting forwards down the flight path. We can experience these forces physically by riding a bicycle up and down a hill. Going uphill, we must increase thrust to balance the proportion of our total weight acting backwards down the hill. If we shed even a small fraction of that weight and deprive it of thrust, we can see what happens to it. Going downhill, the opposite applies. We have to reduce thrust to avoid excessive speed, and the discarded weight will continue forwards down the slope. Once we leave the ground behind, however, no matter where we point the aeroplane, one of the 4 forces acting on it, weight, always acts in one direction, straight down. All the rest of the geometry of flight revolves around that central fact. And so, when we want to climb, we have to offset the effect of weight acting partly backwards down the flight path by increasing thrust, just as we have to pedal harder to ride a bicycle up a hill. When we want to descend without increasing speed, we have to offset the effect of weight acting forwards along the flight path and decrease thrust, just as we have to on a bicycle going downhill. Beyond a certain angle, the descending flight path becomes a glide. There is now enough weight acting forwards along the flight path to keep the forces in balance, and thrust as such is no longer needed. Even in this situation, the forces remain in balance and a steady speed is maintained on the glide path. But the proportion of weight acting forwards along the flight path is now sufficient to act in place of thrust from the propeller and to equal drag. As soon as the aeroplane is leveled out again and power is restored, the 4 forces resume their normal pattern for steady level flight. In everyday flying, however, the aeroplane has to be maneuverable in all 3 dimensions. It can be deflected from straight and level flight in the pitching plane around the lateral axis with nose lifting or dropping like this, in the rolling plane with the wing tending to roll the aeroplane around its longitudinal axis, in the yawing plane around the vertical axis, or in any combination of the three. How can this capability be reconciled with a reasonable degree of stability in straight and level flight? Stability is a complex subject, but its basis lies in the plan form of the aeroplane and the arrangement of its flying surfaces. In the pitching and yawing planes, stability is assisted by the tail surfaces exerting leverage along the arm provided by the fuselage. If we look at these tail surfaces, we find a horizontal tail plane and a vertical fin. Let's see how they help stability. To begin with, the four forces seldom act from the same point on the aeroplane. Weight is normally arranged to act from a point ahead of lift, in such a way as to create a nose-down moment around the lateral axis, so that when power is reduced, the aeroplane will pitch nose down. As it does so, the download on the rising tailplane will keep the aeroplane in a stable descent at a stable speed and under normal control. But no matter how stable the aeroplane, the air it flies through is often unstable. Local changes in pressure and temperature cause gusts and currents, which vary the speed and direction of the relative airflow, vertically as well as horizontally. They can thus cause local variations in the angle of attack. When a gust causes a pitch-up moment about the lateral axis, the angle of attack increases momentarily, and so does lift. But inertia, the tendency of an object in motion to keep on going in the same direction, will prevent an immediate change in its flight path. Meanwhile, the tailplane experiences an upload, levers the tail upwards, and slightly overreacts. The aeroplane is now slightly nose down. The tail now reacts in the opposite direction, and through several brief oscillations damps out the disturbance, and the aeroplane returns to level flight. A gust striking at an angle to the flight path can make the aeroplane yaw about the vertical axis, and here the vertical fin comes into play. As it swings out, the airflow provides an opposite reaction to the action of the gust. And once again, oscillations will occur before the fin succeeds in damping out the disturbance. Gusts also disturb the aeroplane around its longitudinal axis by varying the angle of attack as between one wing and the other, and causing it to roll. In this case, the stabilizing influence is the change of incidence affecting the two wings. The wing that is dropping experiences an increase in the angle of attack and thus an increase in lift. This will stop the roll, but will not level the wings. At this angle, total lift at right angles to the wing is acting slightly in the direction of the roll, while weight acts downwards through the center of gravity. The aeroplane therefore moves in a side slip in the direction of the roll. In a high-wing aeroplane like this one, the roll and slip is largely corrected by the effect of having the fuselage below the wing, and this will help the pilot to level the wings. In the same situation, a low-wing aeroplane relies more on the angle at which the wings are inclined to the horizontal, known as the angle of dihedral. When the aeroplane rolls, lift increases on the down-swinging wing and decreases on the up-swinging wing, so the roll stops. Lift is now acting slightly in the direction of the roll, and weight acts downwards. So the aeroplane side slips. Thanks to the dihedral, the relative airflow now strikes the lower wing at an angle of attack greater than that at which it strikes the upper wing, which will be slightly blanketed by the fuselage if the side slip persists. Once again, the pilot must correct the slip and level the wings. No aeroplane is fully stable laterally. And if an involuntary roll of more than a few degrees is left uncorrected, the lift from that powerful wing acting at an angle to the aeroplane's path will pull it into an unstable, descending turn. To recover from it, we must use the controls.